Now that we have the constant coefficient equations down, the next thing we need to do is look at a new type of differential equation that's called a Cauchy Euler equation. And we're going to use a lot of the same tactics that we use to solve the constant coefficient linear equation. First, we'll solve the homogeneous version, then we'll solve the non-homogeneous version. And we're going to do a lot of this by algebra. Again, similar to what we did with the constant coefficient equation. So first, let's look at what a Cauchy Euler equation is. And so here's an example. So if you look at the equation, it looks a lot like our standard linear equation that we've been dealing with, but there's one key here, is the coefficients. And so it still has to be linear, because we're still talking about linear here. So all the derivatives, if you notice, all the derivatives of the first power, also all the functions that are coefficients are functions of x here, but there's specific functions of x. Notice that the coefficient here is a power function of the same degree as the order of this derivative. And here this is a power function of the same degree as this derivative, etc., the whole way down. Okay? And so that's what really makes a Cauchy Euler equation distinct, is that the coefficients have the same degree as the order of the derivative. So it's made up of power functions, and the power functions and the derivatives match up in their order. So here's an example of a second order. Notice that we have ax squared, second derivative, bx to the first derivative. There is no x, just a constant, and we don't have a derivative, we just have y. And so that's going to be the pattern that makes up a Cauchy Euler. If you were to look at, say, a third order, it would be ax cubed times the third derivative plus bx squared times the second derivative plus cx times the first derivative plus d times y equals 0 if it's homogeneous, or equal to g of x if it's non-homogeneous. And so it has to have that specific form to be Cauchy Euler. If any of this is not right, let's say this is fourth power here, then this is no longer Cauchy Euler. So it's a very, very specific type of equation. All right. So then when we did constant coefficient equations, and the difference with constant coefficients is we wouldn't have these powers here, okay? These power functions wouldn't be here. It would just be a y triple prime, b y double prime, c y prime. They would just be constants only. But now we have those power functions. So when we did the constant coefficients, we saw that exponential functions solved the constant coefficient equations. Well, by looking at the coefficients, we should probably make the assumption that exponential functions probably won't get the job done here. What more likely would probably work would be a power function, would probably be a better type of function that could possibly be a solution to these Cauchy Euler equations. So what we're going to do is we're going to look at the second order one. And we're going to make an assumption that x to the m, where m is to be determined, is going to be a solution to this Cauchy Euler equation. So let's plug it in and see what happens, similar to the tactic we took with the exponentials. And then what we're going to determine is that there will be power function solutions based off of m, what m's are we going to use, etc., and we go from there. All right, so if we say y equals x to the m is the solution, then the derivative would have to get plugged in, which would be m x to the m minus 1, just using power rule. And then the second derivative would also have to get plugged in this case m times m minus 1, x to the m minus 2. Again, second derivative, just using power rule again. So if we look at this Cauchy Euler, and for y double prime, we plug in the second derivative, and for y prime, we plug in the first derivative, and for y itself, we plug in y. We're going to end up with this, ignore this minus 1. That shouldn't be there. Okay? And so, yeah. So then what we're going to get is, I don't know where that minus 1 came from. So then what we're going to get is, if we multiply this x squared here with this other x to the m minus 2, what happens is the exponents add, and you have a plus 2 and a minus 2, which will cancel them out, just giving me x to the m. If the same thing happens here, that's where the minus 1 should be. The minus 1 should be right here in the exponent, because it should be x to the m minus 1, like we have here. So then these two would cancel out as well, because you add 1 and subtract 1, just giving you x to the m. And then finally, this one would just stay x to the m. Well, notice they all have an x to the m in them, so we'll factor an x to the m out. And then we'll have this a times m minus 1 plus bm plus c. So then we'll distribute this out, and what we're going to get is am squared. We're going to get a minus am and a plus bm, so that gives me b minus am plus c, x to the m. Now what we have here is zero product property again. We have this times this equal to 0. Well, that means one of these two things has to equal 0. So either this equals 0 or x to the m equals 0. Well, the x to the m equaling 0 again does nothing for us, because if x to the m equals 0, that just tells us that y equals 0 is a solution, which we know is always going to be a solution to a homogeneous. So then this is what we want to look at, is when is this quadratic going to equal 0? And ultimately what we're trying to figure out is what m's will solve that quadratic equation. Well, this is no different than what we've seen before, only that this is now our auxiliary equation for Cauchy Eulers. Notice this auxiliary equation is different from the auxiliary equation we had with constant coefficients, which was just am squared plus bm plus c equals 0. Where a, b, and c came from the original differential equation, and the same thing here. A, b, and c all come from the original differential equation that looked like this. So we have a different auxiliary equation. The big difference sits right here in the linear coefficient. Once we have that, though, we know that if we solve this for m, there are 3 possibilities. And once we figure out what m is, then y equals x to the m should solve the differential equation. So we break it down into 3 cases. Case 1, m is 2 distinct roots. When you solve a quadratic, you can get 2 distinct real roots. So m1 and m2 are real numbers. They're not equal to each other. So that means y equals x to the m1 is one solution, and y equals x to the m2 is a totally different solution. Those solutions would be linearly independent. We could check that by looking at the Wronskian. I believe we did do that in the first lesson of this unit. So they form a fundamental set, and therefore the general solution should just be c1x to the m1 plus c2x to the m2. Pretty simple. So here's an example of that. So if we look at this here, a is 1, b is negative 2, c is negative 4. In the Cauchy Euler, notice this is Cauchy Euler in that this power and this derivative match up, and there's no x to a power on the last one. And so if we use our auxiliary equation, am squared plus b minus am plus c equals 0, we would get m squared. B minus a would be minus 3m minus 4 equals 0. So that's factorable in that we would get m minus 4, m plus 1. So m equals 4 and m equals negative 1. 2 distinct real solutions. Therefore, y equals c1 x to the 4th plus c2 x to the negative 1 solves the differential equation. Pretty simple, not that hard. Still just using basic algebra, understanding how we form our solution here. The difference being, 1, Cauchy Eulers have a different auxiliary equation. There's the big difference. 2, Cauchy Eulers have power functions as their solutions, not exponential functions. So know how to use the m values to form the solution to this new type of differential equation. Now, case 2 is when we have the repeated real roots. So if m1 equals m2, they're real. okay, and they equal each other. So y equals x to the m1 is one solution, but y equals x to the m2 would be the exact same solution again, so we can't have that. So what we want to do is we want to look at, well, what's the second solution? Well, remember, we have a formula that will generate the second solution. First off, understand that the discriminant would be 0 in this case, and m1 would end up equaling negative b minus a over 2a if we use the quadratic formula in our Cauchy Euler auxiliary equation, which remember is am squared plus b minus am plus c equals 0. Essentially, in the quadratic formula, this whole thing would take the place of where the b is in the quadratic formula. And this would yield what m1 would actually end up equaling, because the discriminant would be 0. So then if we use the reduction of order formula, we first have to put the Cauchy Euler in standard form to do it, which would make our p of x, which is this piece right here, equal to b over ax. So if we did the integral of p of x, which would be the integral of b over ax dx, that would be log of x to the b over a. Technically, we would have b over a log x, and then we could bring that in as a power, so that's what we end up with. All right, so then our second solution, so let's say y sub 2, is what? It's the first solution, which is x to the m1 times the integral of e to the negative integral of p of x, okay, over x to the m1 squared, so x to the 2m1. Well, if we bring that up to the numerator here, we also cancel this by bringing this exponent in here as a negative 1, bring that in, and then we would actually multiply it by this current one. E and the log cancel, so you get x to the negative b over a. You also have x to the negative 2 m1, but remember m1 equals this, so if m1 equals that, we simplify, we eventually get down to just x to the m1 times the integral of dx over x. Well, that's a logarithm integral, so the second solution should be x to the m1, which is the first solution, times log x. So the idea here is we get an extra log x attached to the first solution as our second solution. If we were to do this for higher orders and it was repeated 2, 3, 4 times, what we're going to be doing is stacking an extra logarithm on. So the first time it's repeated, x to the m1 log x. The next time would be x to the m1 log x squared, so there'll be 2 extra logs. Then the next one there'll be 3 extra logarithms, so log x cubed, etc. Remember, log x squared is not the same thing as log x squared. Okay? So in this example here, fairly simple. We have a Cauchy Euler. We have an a of 4, a b of 8, and a c of 1. So if we use the auxiliary, am squared plus b minus am plus c equals 0, we would get 4m squared plus b minus a would be 4m plus 1 equals 0. This would factor as 2m plus 1 times 2m plus 1 equals 0. So then we get m to be negative 1/2, but it's repeated twice. So since it's a repeated solution, the general solution should be c1 x to the minus 1/2 plus c2 x to the minus 1/2 times log x. So every time it's repeated, log x. Case 3, complex conjugates. So m1 equals alpha plus I beta, m2 equals alpha minus I beta. So technically we could write this as c1 x to the m1, alpha plus I beta, c2 x to the m2, which is alpha minus I beta. They are different solutions. They are linearly independent solutions. Unfortunately, what it creates is complex function solutions. So we really would like these in terms of real functions. So what we're going to do is the same thing we've done before. we'll use Euler's formula. We're going to do a little bit of computation with Euler's formula. In the end, what's all that matters is that we end up with this right here, where alpha and beta come from the complex conjugates. Notice it's somewhat similar to the setup we had with the constant coefficient ones. In this case, though, it's based off power functions, and we have logarithms in here. So x to the alpha, c1 cosine beta log x plus t2 sine beta log x. And so if we were to solve this Cauchy Euler, let's ignore these initial values for a second, but let's just solve this Cauchy Euler here. A is 4, C is 17. Notice there's no y prime, so in that case B is 0. So we could always write 0x y prime there inside here, and it's still going to be the same equation, just you see that there would be a b of 0. So we're going to get 4m squared minus 4m plus 17 equals 0. Then we can use quadratic formula to solve for m, in which case we're going to get 4 plus or minus the square root of 16 minus 4 times 17 all over 2 times 4. So what this is going to give us is 4 plus or minus 4i over 8. So 1/2 plus 1/2 I. So alpha is 1/2 and beta is 1/2. And what that would then give us is the solution of y equals x to the 1/2 times c1 cosine of 1/2 log x plus c2 sine of 1/2 log x. Then what we could do is additionally solve now the initial value problem. So in this case we have y, but in this case we have y prime. So we would have to take the derivative of this equation here to figure out what y prime equals. And then we would be able to plug in that x is 1 and y is -1 from here. And then here we would plug in that x is 1 and y prime is -1/2. And that will help us find C1 and C2. So our y prime would be 1/2 x to the minus 1/2 times C1 cosine of 1/2 log x plus C2 sine of 1/2 log x plus, it's product rule here I'm doing, x to the 1/2 times the derivative of the inside here, in which case it's going to be a chain rule and a chain rule. So it's going to look pretty messy, but we're going to get through this pretty easily still. So what would we have? We would have derivative of cosine is negative sine, so we'd have negative C1 sine of 1/2 log x times the derivative of the 1/2 log x would just be a 1 over 2x. Okay. Then the next piece, we plus C2 cosine of 1/2 log x times, again, 1 over 2x. That's times. And I squeeze it in here, so it's not going to look great. But we're going to be plugging in 1 for x. Well, the nice thing is log of 1 is 0. So a lot of this is going to clean up, in which case we're going to get, on the next slide, I'll finish it off. So let's finish up this initial value part. So we have the y, let's rewrite this, y equals x to the 1/2 times C1 cosine of 1/2 log x plus C2 sine of 1/2 log x, right? And that was the solution to the differential equation, but we're also going to need to know what y prime equals. And so we get that y prime equals, was this 1/2 x to the minus 1/2 times C1 cosine of 1/2 log x plus c2 sine of 1/2 log x plus x to the 1/2 times, let's put it down here, what was it, minus c1 sine of 1/2 log x times 1/2x plus c2 cosine of 1/2 log x times 1/2x. Alright, our initial values were that y of 1 equals -1 and y prime of 1 equals -1/2. Alright, so if we use the first one, y of 1 equals -1, so y is -1, x is 1, so 1 to the 1/2 is 1, times c1 cosine of, remember log of 1 is 0, so this will be cosine of 0, plus c2 sine of 0, and since sine of 0 is 0, and cosine of 0 is 1, this gives us a -1 equals c1, and so we got c1. Now if we use the y prime of 1 equals -1/2, y prime is -1/2, and x is going to be 1, so we're going to get 1/2 times 1 to the -1/2, which is 1, times, again, log of 1 is 0, right? So this is 0, this is 0, this is 0, this is 0. And so we're going to end up with c1 cosine of 0, which is going to be 1, plus c2 sine of 0, which is 0. So we're just going to get that, plus x to the 1/2, which is 1, times, again, sine of 0, which is 0, so this whole thing is 0, so that's gone, plus c2 cosine of 0, which is 1, times 1/2x, so 1/2. All right. Now remember, we know that c1 equals -1, so we end up with -1/2 equals 1/2 times -1 plus 1/2 c2. And so this is -1/2, so if I add -1/2 over to the other side, I'm going to get 0 equals 1/2 c2, which is going to tell me that c2 equals 0. So fill all that in to the original solution. We get that y equals x to the 1/2 c1, which is -1 cosine of 1/2 log x, plus c2, but c2 is 0, so then that's the solution to the IVP. It wasn't really that big of a deal in terms of level of difficulty. I mean, it's just long in that doing this derivative for y prime, you had to keep track of what you were doing. But other than that, you're just plugging numbers in. So you should be able to do these initial value problems. All right, let's do another Cauchy Euler equation. Okay, in this case, we have a third order Cauchy Euler equation. X to the third derivative, x to the second derivative, x to the first derivative, and then we have our y with a constant in front of it. Now what we would need to know is what the auxiliary equation for a third order Cauchy Euler equation is. We haven't come up with that. We should assume that it's going to be slightly different than the auxiliary equation from the constant coefficient ones, because the second order one, the auxiliary equation, was different. So we can do it two ways. One is we can just come up with the auxiliary equation that relates exactly to this equation. The problem with that is that if we have another third order Cauchy Euler, we would have to create the auxiliary again for that one. Or what would be more beneficial would be to just figure out what the general auxiliary equation for all third order Cauchy Euler equations would be, and then we can use that over and over. So that's what we're going to do. So how do we do it? Well, we do it the way we came up with the second order Cauchy Euler equation auxiliary before. We said that y equals x to the m should satisfy this equation. We're trying to figure out what m's will actually do that. So then in order to do this, we have to plug this in and see what happens. So then we also have to find the derivative, which is m x to the m minus 1. And then the second derivative, which is m times m minus 1 times x to the m minus 2. And then the third derivative, which is m times m minus 1 times m minus 2 x to the m minus 3. And this is the new piece, we have to plug that in as well. We plug all this in for the corresponding derivatives and then see what comes out from that, and that'll give us our auxiliary equation. So what do we have here? We have a standard Cauchy Euler that I'm going to work with, which is a x cubed y triple prime plus b x squared y double prime plus c x y prime plus dy equals 0. And so we're gonna plug all this into the standard one, and then we'll apply what we get out of this to this specific one. And so a, b, and c are your constants. Okay, in this equation they're going to be 1, 5, 7, and 8. So if I plug in my derivatives into the equation, I get ax cubed times y triple prime, but y triple prime is m times m minus 1 times m minus 2 x to the m minus 3 plus b x squared times m minus 1 x to the m minus 2 plus c x y prime, which is m x to the m minus 1 plus d x to the m equals 0. All right. Now, a lot of this is going to work out the same way, and that worked out with the second order, x cubed, x to the m minus 3. That's going to just give me an x to the m when I add those exponents together. This x squared and this x to the m minus 2 is just going to give me an x to the m. This is going to give me an x to the m, and I have an x to the m here. So ultimately, I can pull the x to the m out of the whole thing, and I'd be left with a times this, b times this, c times m, and then d. Well, I'm going to actually have to multiply this out. So if you do these two, you're going to get m squared minus m, and then multiply it times the third one. What are you going to get? You're going to get a times m cubed minus 2m squared minus m squared plus 2m. Here you're going to get b times m squared minus m plus cm plus d. Now, this is actually going to give me 3m squared. So now if I start grouping like terms, we get x to the m times am cubed. We're going to get 3am squared, and we have a bm squared, so minus 3, sorry. So we're going to get b minus 3am squared plus, we're going to have an 2am minus bm plus cm, so 2a minus b plus c m, and then we have a d equals 0. Well, we've seen that this x to the m is equaling 0 does nothing for us, which tells us that this is going to have to equal 0, and that is exactly going to be your auxiliary equation for your third order Cauchy Euler equation. So now when we do this ever again, anytime you have a standard third order Cauchy Euler equation like this, where a, b, c, and d are constants, we know that this is going to be our auxiliary equation that needs to be solved. And then whatever m's come out of that, well, m could be real, n could be repeated real, n could be complex conjugates. There's always going to be 3 solutions, and any combination of those 3 things can happen with those 3 solutions, and we'll come up with the answer. So now let's look at this specific example and apply that. All right. X cubed y triple prime minus 5x squared y double prime plus 7x y prime plus 8y equals 0. That's what we're trying to go after. In this case, a is 1, b is negative 5, c is 7, d is 8. I'm sorry, this is plus 5, so b is 5. All right. So our auxiliary equation should be am cubed plus b minus 3am squared plus 2a minus b plus cm plus d equals 0. In which case, a is 1, so this will be m cubed plus, oh man, my computer's all over the place today, plus b minus 3a, so in this case that's 5 minus 3 times 1, so 5 minus 3 is 2, so 2m squared plus 2a, so that's 2, minus 5, which would be negative 3, plus c, which is 7, will give me 4m, plus d, which is 8, equals 0. All right. And so now that's the cubic polynomial that we need to factor in order to solve the equation. Well, if I factor an m squared out of the first 2, I'm going to get m plus 2. M plus 2. And if I factor a 4, I'll get an m plus 2 out of the second 2 terms. Now they both have an m plus 2, so then I'll get m squared plus 4. So this is going to give me m equals negative 2 as one of the zeros, and this one's going to give me m equals plus and minus 2i. So complex conjugates here, alpha is 0, beta is 2. I have 3 solutions total, 1 real, 2 complex conjugates. So my solution to the differential equation should be C1 x to the negative 2 plus C2 cosine of 2 log x plus C3 sine of 2 log x. And there's your solution to your differential equation. All right, now here we have a second order Cauchy Euler again, but here's the big difference. Now it's not a homogeneous, it's a non-homogeneous one. So the way we're going to solve this is through variation of parameters. You might think, oh, well, this is a function that can be annihilated, so why don't we try the annihilator method? The problem with the annihilator method, remember, is that it only works if we have a constant coefficient differential equation. We don't have that. The only way to solve the Cauchy Euler ones right now would be with variation of parameters. You cannot use the annihilator approach for this. So, first step, we want to find y sub c. So we solve x squared y double prime minus 3xy prime plus 3y equals 0, in which case we're going to get our auxiliary equation to be m squared b minus a, so in this case it's going to be minus 4m plus 3 equals 0. That's going to then give us m minus 3, m minus 1, so m equals 3 and m equals 1. So our solution to the homogeneous equation is going to be C1 x to the first plus C2 x to the third. All right, so that's y sub c. Now, in that, our first solution is x, our second solution is x cubed, the derivative of the first solution is 1, the derivative of the second solution is 3x squared, and remember from the original differential equation, if we put this in standard form, we have to figure out what f of x equals for our variation parameters formulas, but this has to be in standard form, so we would have to divide by x squared all the way through to do that, and therefore our f of x would end up being 2x squared e to the x. That's a pretty important step right there. That's the part that a lot of people will mess up, is they won't simplify this and get 2x squared e to the x. They'll just look at it and say, okay, here's f of x, but you've got to remember the steps from variation parameters. You have to have your equation in standard form to find your f of x. And it matters so much more now with the Cauchy Eulers, because you're not just going to be dividing by a constant here, you can be dividing by a power function, which is going to drastically change f of x. All right. So now our second step is to find y sub p, in which case y sub p is u1 y1 plus u2 y2. And we find u1 by first finding u1 prime. So u1 prime would be minus y2 f of x. This is an x. E to the x over this times this minus this times this. So that'll be 3x to the fourth, or sorry, 3x to the third minus x to the third. So ultimately, what do we get here? We get minus x cubed times 2x squared e to the x over 2x cubed. So what you'll see is that this x cubed here and this x cubed will simplify. These two 2's will cancel. And so we end up with u1 prime to be negative x squared e to the x. So then we need to find u1 by integrating negative x squared e to the x dx. We'll do that by parts, but we can use tabular method to get that answer, in which case we're going to say negative x squared and e to the x are our u and our dv. So we'll differentiate negative 2x, negative 2, 0. This will be e to the x over and over again. Match them up on the diagonal, plus, minus, plus. And this is all your integration by parts from Calc 2 in the tabular method. Use that to put the answer together, which we would then get, what, minus x squared e to the x plus 2x e to the x minus 2 e to the x. So there's u1. u2 prime first is going to be y1 f of x, so x times 2x squared e to the x over the same denominator again, which remember was 2x cubed when we've multiplied this determinant out. And so you're going to get this 2 and this 2, this x cubed and this x cubed to cancel. You're just going to get e to the x. So then u2 is very easy to find. It's the integral of e to the x dx. So u2 is just e to the x. All right, so now we have u2, we have u1, we build our y sub p by doing u1y1 plus u2y2. So if y sub p equals u1y1 plus u2y2, we would get u1, which was negative x squared e to the x plus 2x e to the x minus 2e to the x times y1, which was x, plus u2, which was e to the x, times y2, which was x cubed. If we distribute this x in here, here, and here, notice we're going to get a negative x cubed e to the x out of this, and we have a positive x cubed e to the x. They're going to cancel. We're also going to get a 2x squared e to the x and a minus 2x e to the x. So there's your y sub p. So then, to build the final answer, we should have y sub c plus y sub p, in which case y sub c was, remember, c1x plus c2x cubed, and y sub p is 2x squared e to the x minus 2x e to the x. And there's your solution to the second order Cauchy Euler non-homogeneous equation. So remember, if we're going to solve a non-homogeneous Cauchy Euler equation, the only way to go about it is variation parameters. If you try to use the Annihilator method, you will have an issue because the Annihilator method will only work for constant coefficients because the annihilators have constant coefficients only. If you introduce that into a Cauchy Euler equation, you will no longer have a Cauchy Euler equation or a constant coefficient equation. You'll have some weird mix which we don't know how to solve. So variation parameters is the way to go.